and thank you, Karen, also for the very good presentation. And I'm going to present a work that I like very much this photograph. In this photograph, we see a microbial here in the upper part, and this microbial was caused by a fault. And we are seeing here the fault surface, and what Lenin here is showing is that this fault surface is full of minerals, and these minerals are mainly calcium carbonate in the form of aragonite. So when the fault moved, it revealed the fault surface, and we could see this beautiful mineral formations that is directly related to the formation of microbial biolites. So the question, this is our work group. Mainly, what I'm going to present is the work of Janet Sanchez, who finished her PhD in 2023. And right now we have two projects that are beginning. And I also want to say that la Coordinación de la Investigación Científica de la UNAM supported this conference. So the question is, do microbes have a role in mineral or sediment formation? And the answer after the last presentation is that yes. Microbes can induce mineral precipitation, they modify pH, they produce cellular polymeric substances, and they use mineral for this biomineralization. And these processes can strongly impact the soil aggregation, the mineral weathering, and the overall health of the ecosystem. So it is very important in the new studies that we integrate the geological and geophysical data together with your chemical and microbiological data. And this is the main goal of this presentation. So, okay. So the ecosystem is formed by the climatic diversity, by biodiversity, which is what more of you study, and by biodiversity. All of these conform in nature, and it has function, and he was supporting services or ecosystemical services. And geodiversity is composed from the geology, the relief, the geomorphology, the soils and sediments, and more importantly, water, surface and underground water. And it is very important to recognize that geodiversity supports biodiversity. I like very much this graph. It's showing in the bottom the plate tectonic settings. Subduction zone is here. Here we have a volcanic arc. We have the spreading ridges in the mid-oceans, passive margins, deserts, and other environments that are driven by tectonics. And we can see that microbes are everywhere. They live in hydrothermal deep sea vents and up into the volcanoes, as Karen has shown now, and in the background basins or deserts in those regions, and also in the subsurface. So, but the distribution is not random. The distribution is controlled by the geological setting. So the idea is that geology is controlling the ubication and diversification of microorganisms. But this is very important to recognize. So I'm going to present the result that we have had in this crater, Rincón de Paragueo, that for us it has been a natural laboratory to study geological processes in the last years. It's a small crater that has an internal lake that has been desiccated in the last 40 years. And as you can see, we have a wall around that makes this an endorheic basin. And these walls there's a forest in these walls, but in the middle of the crater there's sediments that are white. This is an image from Google Earth of the region. This is the village of Valle de Santiago, and the region is in the central part of the Trans-Mexican volcanic belt at the northern part in a volcanic field that is called the Valle de Santiago volcanic field. And as you can see here, there are many of these craters aligned in this direction and also in an east-west direction. And Rincón de Parangueo is right here. And we can see that it's the only one that has these white colors inside. This is a digital model, a digital elevation model of the area, and we can see that there are many craters that form in the area. We can see that Rincón de Parangueo is putting on an older crater here in this area and here. And until last year, we thought that it had formed. It has less than 137,000 of years, but several new ages suggest that these volcanoes are very young, from 24,000 to 11,000 years before the present. Valle de Santiago has an altitude of 1,700 meters above sea level, has a diameter of about 1 kilometer, and the conductivity in the water has increased in the last year. The pH has also increased up to 11 that we measured 1 month ago, and the maximum depth of the lake was 2 meters in 2008, and last year it completely was desiccated. A mar is a volcano that is formed because the magma is flowing toward the surface and it encounters an aquifer, and when the magma touches the water, it explodes violently and forms a crater. The deposits are generally put aside, around the crater in what is called a top ring, and in the central part of the crater is very common that we have lakes that are controlled by the water table at the time of the explosion. And as you can see, the magma flows in that direction, rupturing the rock. So there's always a good hydraulic connection between the geology around and the zone of the crater. So the crater formed about 24,000 years ago, and very fast the lacustrine system was set up, and the sedimentation in the central part of the crater began. And here we can see the internal structure of the lake is composed of layers of, here is the scale, the subcentimetric layers or millimetric layers of carbonaceous deposits and organic matter. In several occasions we can see sandy deposits, and this is a borehole that we have collected in the central part of the crater, and Yesenia Villegas is going to present a poster on Friday. From the information that there is in the crater, we have Barbara Mogel did this age model, and we can see that in the central part of the crater, the sedimentation rate is about 0.7 millimeter per year, while in the margin of the crater, the sedimentation is a little higher, 1.4 millimeters per year. So if we see the oldest age that we have is about 22,000 of years, so the start of lake sedimentation started very, just very fast after crater formation. The lacustrine system was active until the decade of the 1980s in the last century, when it began to decrease its level progressively. This is 1983, and this is 2006. And the reason of the decrease of the water level was the extensive agriculture that is going on around the crater. So here we see the Rincón de Parangueo crater, and all of these points are agricultural wells that extract water. Here we can see the piezometric level descent that is about a half of a meter per year, and it's more or less the same rate at which the water descended in the crater. Once the lake was desiccated, then began the process of land subsidence, and a lot of fractures formed in the crater, and these fractures provoked the ascent of the surface of the crater down to 20 meters from the original level. Vania Ferrer did a measurement 2 years ago, and we have that there has been a descent of the surface of the lake of 22 meters in 42 years. So more or less a half of a meter per year, which is coincident with the lowering of the regional activity. For us, geologists, it's fortunate that the lake desiccated, because we can make mapping of the carbonates, and what we see is that we have a distribution of concentric bands with a oncolite platform. These green rocks that we see here are microbialites that are aligned around the crater, and the red lines are the subsidence faults that form. The pelagic sediments are in the central part of the crater. These are views of the central part of the crater. This all white sediments. This is the fault that is around. These are the remnant of the ponds, and we can see a lot of sedimentary structures around the crater. One of the side effects of the land subsidence is that the compression or the scleral compaction of the sediment provoked the formation of several domes of mud, or let's say mud volcanoes, that have different sizes in the central part of the crater. One interesting thing about Rincón de Parangueo is that the measurements of the gassing in the soils yielded that there's a flow or the gassing of CO2 of about 10 tons per day. Flow of methane, and also flow of sulfurs or sulfurs. And the isotopic composition of the methane suggests a biogenic origin, but the isotopic composition of the CO2 suggests a mixing of of a mantle source and a surface source. And here you can see the distribution of the measurements, and you can see that there are hot spots where gas is coming out of the crater. Inside the crater, we see beautiful microbial around the annular faults, and we also see microbial mats in the central part of the bones. Here, this is a microbial mat that we collected a month ago, and we can see that there's a growing of different minerals, mainly gypsum and salts. So we sampled different compartments or different niches in the crater, mainly the microbial mats that we saw in the microbial sediments, the water, and we also made several boreholes to collect samples in the central part in the pelagic sediments. Down to 4 meters, and we have now a borehole of 10 meters. And of course, we have a lot of microorganisms comprising bacteria, eukarya, and archaea. I'm not going to talk about this, but there are several posters in the sessions, and we can talk more about that. I'm going to focus on the composition of the sediments. These are the microbialites, and when we make X-ray diffractions, we see that most of these zones are composed of hydromagnesit and aragonite. And the aragonite has 2 main habits. This one that is like a needle, and this one that is it's called botryoidal, and it's like little bubbles of aragonite formed in this region. If we cut the microbialites, we see that they have a thrombolytic structure in the central part and a stromatolitic cross in the stromatolitic cross.
You have a minute to go.
Around the annular fold, we see this evidence of degassing, forming chimneys, like those vents in the ocean. These are the equivalent in the crater. Here is seeping gas out of the crater and forming microbial communities around. These are formed mainly by aragonite and some gypsum. And this is another view of the vents. In the water, the microbial mats are composed, besides the microorganisms, of salt, mainly tron, thermonatrite, and halite. Here you can see the crystals that are formed in these graphs. And in the sediments, these are the several views of the pelagic sediments. We found a distribution of different physicochemical factors and the abundance of the microorganisms varied around the profile. For us, it was a surprise that 4 meters below the surface, we found a lot of organisms living in the mud. And here we can see evidence of what we consider are organisms in this layer of mud. And we think that these microorganisms have a role in the formation of methane in this gas. So the general model that we have is that we have the crater that has interaction with the regional aquifer. We have a source of groundwater flow, heat, and CO2, and we have a complex microbial system that is composed with different communities that live at different levels and that can sequestrate CO2 and the gas methane. Okay. The conclusion of this talk is that geology has an important role in the development and diversification of the microorganisms. So we have to consider geology, that the microbial communities can vary across geological limits or interact with geological processes at different scales. And very important that microbial communities in the subsoil can be affected by these processes. And then if we know the history of a place, then we can understand the history of these microbial communities. And that is all. I want to only announce that we are going to make a field trip on Sunday and to several sites of geological interest around Patrocínio.
In the time we move to the next presentation, maybe you have some couple of questions for Mariano.
Ay, ya me había saludado.
Or for Karen. No, I finished my job here. Some questions?
That was really interesting about the methanogens. Do you think they're using hydrogen and CO2 that's from the magma degassing? Okay, that's very good. What is the Delcy 13 of their methane pool? Yeah.
No, we have measured.
Oh.
But definitely,
Yeah.
the volcanism is very young. Geologically, 24,000 years is
Yesterday.
Yesterday. And this is very new from the volcan Paricutin. Volcan Paricutin made the eruption 80 years ago, so everything is active in the geological context.
Yeah.
Great talk, thank you so much. Do you see only the microbialites are over there in the crater? Do you only see trombolytic textures? Do you see any other kind of the diversity of textures there, or just trombolytes in general? They are.
The microbes are everywhere. Yeah, I think of Ricardo Carandeo as a complete microbiome. You have your stone, that is layer microbialites. You have trombolytes. You have stromatolic crust, but also you have oncolots, and there are colonization of the microbes on trees, rocks, everywhere. They are growing with many different textures.
And it's only, you say that you only found an argonite in this?
No, we found hydromagnesite,
Okay.
aragonite in the microbialites, and a lot of salt in the pelagic sediment.